Hello and welcome back. In this video, we'll have a look closer behind the scenes of how Python does certain things when we deal with objects we can iterate over and special functions like decorators and generators. So let's look at behind the scenes of the iterators. So we have previously seen that we can iterate over items, for example, in a dictionary or a list. So for example, if we had a list, my list, and we had elements in this list, cat, dog, or bird, and then we can just iterate over them by saying for items in my list, we print an item, and this is what we return. So this loop iterates over all the elements in the list and gives us access to each element in turn, and then it stops once we reach the end of the list. This is very convenient. We could do this manually by creating an iterator object and then using this to traverse the list until there are no more elements, and then a stop iteration exception is raised. So we do this by defining an iterator with the keyword iter, and then proceed with the next item with next. So the equivalent of the above would be to have my list again. Then we define an iterator. My iter is an iterator over my list. And then we say we try this statement until it fails, and we just continue indefinitely, at least until we hit an exception, and then we print what comes back from my iter. And then we accept the stop iteration exception that is raised at the end of the list, and then we just recover gracefully from this and say we reach the end of the list. And then if we do this, we have cat.bird, and then reach the end of the list, and this is only here because we have the print statement. Now, obviously, this is quite a horrible way, an unpythonic way to loop over a list. Some programming languages will make you do something like this, though. But there's one situation where we do need to think about such iterators. And this is when we need to define the class that we can iterate over. So then we need to implement this kind of magic ourselves. In particular, we need to implement the magic or dunder functions iter and next to define the behavior of what happens when we want to iterate over a class. Remember that these double underscores before and after the keywords indicate that we should not call these methods ourselves, and instead the iter and next methods tell Python what to do when we try to iterate over our class. So for example, we may need to develop a more fancy list or a counter or a more powerful dictionary or whatever it is than the standard methods provide. So say we want to implement a class counter, and we need to be able to iterate over this counter. So here we have the magic or dunder method init. We have a start and stop parameter that we give it. And now we need to implement the magic functions iter and next, and then define how the class will behave. So in iter, we return the class itself, and for the next method, we first of all check if we reached the end of it, like the stop number, for example, here, and then raise the stop iteration exception. And if we're still good, and we haven't reached the end of our counter, then we increment 1 and return the current counter. So that's how we use our class, right? We initiate it. This is an instant of the class between 0 and 5. So we count 0, 1, 2, 3, 4, 5. And because we have the greater, not the greater equal. And then we can loop with a for loop over my counter. And then we can print the value of the counter. So the value of the counter is 1, 2, 3, 4, 5. So this is one way how we can implement our own objects that we can iterate on. One of the very special functions that we can have in Python are generators. There are special functions that remember their state each time you call them. Remember that with the normal function we've seen earlier, and we call the functions, we do our computations and maybe define local variables, but we return what we have and the function is forgotten. However, in some cases, we may want to remember the state of the functions. For example, if we were to read from a very large file, you don't want to keep it all in memory, but we need to pass the content maybe line by line or in chunks. So it would be very cumbersome to open a file, read one line, remember which line we've read, close the file, open the file again, jump to the next line, and so on. Or another use case is if we want to compute a long list of elements, but we don't know how many elements we want to compute when we start with. We could do this with a for loop or a while loop, but then we will need to define starting and stopping conditions. And if we don't have them, the generators provide a neat way of doing this without having to decide when we need to start. We just repeatedly call the function, and if we stop calling it, we sort of start executing it. So generally, generators are defined very similarly to normal functions. The main difference is the keyword yield. When we encounter a yield statement, the execution of the function will stop. We return the generator object, not the value. This is important to keep in mind. And the current state of the function is saved. For example, we could define the function as an infinite sum. We want to obtain the sum of all integers until we decide to stop. It's maybe not the most useful function, but it illustrates the concept. So we define this function myInfiniteSum. We initialize it with 0. And then we keep going. Now we return with the yield statement sum. Afterwards, we add 1 to the sum. And here we can see the function itself, if we had it as a normal function, would always be initialized to 0. But here, because it's a generator with the yield statement, it behaves differently. So we have the generator, right? We have an instance of this function. And then we just use the next statement, as we've seen with the iterators above. This will then call the next sequence. And we just keep repeating the statement, right? So there's nothing that sort of indicates how often we have called this before. We could also do this in a loop, right? For I in the range of 0 and 5, we call this. And what we can see here is that the function behaves very differently from a normal function. We get 0, 1, 2, 3, 4, 5, 6, 7. And each time we call this next generator, we get another value. You can also introduce a stop criterion that prevents us from reaching the yield statement. And then, as with the iterators above, the stop iteration exception is called at the end. And this is what we do here. Now, if you want to do an optional exercise, rewrite the function for the Fibonacci series as a generator. So you have the generator and the Fibonacci, and then you can just keep on going. It would go look like this in the end. One of the other things that Python allows us is to modify the runtime behavior of function, and this is what's done with decorators. They are sort of higher level functions. They are functions that operate on functions. That concept is a little complex to get your head around, but this really means that we define a function and then change their behavior later without modifying the function itself. So you may ask yourself, why is this useful? But there are many situations where this might be handled. For example, if we want to add an optional print statement for debugging purposes, right? Even though we should really use exceptions, but we can put a print statement somewhere without modifying or clogging up our code. Or we can check the type of the variables we pass to the functions. Or there are other libraries that modify the runtime behavior. For example, there's a handy package called NumPy that speeds up your code, and you don't modify your own function, but use a decorator. So this is where it comes in handy, although it's a bit complex to think about. So the general syntax of a decorator is that it's a special function. We define it again with a def statement. Then we give it a name and inherit from func. And then we define a wrapper, and notice here the arguments with star and double star. So we pass through everything that we would pass to our normal function. And remember, these star and double star arguments mean that we don't know beforehand the number and types of arguments. So this makes it very generic, because everything we pass through this decorator gets passed over through the function. So we can do something before we call our function. And here we then use the function that we would call. And then we can do something after the function returns, and then we'll return the wrapper. So, for example, it would be like we have this decorator start, now the function starts, and we do something, now the function stops, and we return it. So for example, we would define sum a and b returns a and b, and then normally we would do c is the sum of 1 and 2, and that the result is 3. Nothing special so far. Now we use a decorator. There are two ways of calling the decorator. Either we can wrap the function by replacing it with a call to the decorator, or we use a special @ symbol, the name of the decorator, when we define the function. The first approach is a bit clunky and has a bit of code, right? So we do it here. Right? Sum my decorator sum. The other one is a bit more nifty. We say @my decorator when we define the sum. So here we see that we don't actually change anything about our function definition, or we add the decorator here and then we call it. And here we observe the output. This is from the decorator before the function starts. Now we execute it. This is when it returns. And here's the statement in the end. The sum is this. So here we can see that we modify the behavior of the function by just adding the decorator that has been defined elsewhere. We don't modify the function itself, and the only difference is that we use my decorator. That can lead to some very interesting behavior. So as an optional exercise, you could write a decorator for the sum that intercepts the result and just adds 10.